Now let us get into another topic for now, that is cell wall synthesis inhibitors, and we are dividing it into three total parts. This is the first part. For looking at the cell wall synthesis inhibitors, we must know the process of cell wall synthesis. So let us begin with the process. Mechanism of cell wall synthesis. The place, the site where it occurs, it is the cytoplasm, and there are four steps involved in it. First is the formation, next transportation, then transglycosylation or polymerization, then cross-linking. So it has got four steps. The four steps are formation, transportation, transglycosylation or polymerization, then cross-linking. Now for the formation part, let us have a look at the building blocks and the forming materials. So in the first step, that is the formation part, the foundation or the forming material, what is it? Peptidoglycan. And what do we get from this term? Peptide and glycan. What is glycan? Glycan is glycosaminoglycan, and peptido means peptides, that is proteins, amino acids in like in terminology. Now peptides are short chains of amino acid sequences. Now gags, what are gags? Gag is glycosaminoglycans, and what we know is we have got N-acetyl glucosamine. The gag that we have got is N-acetyl glucosamine. That is, we are going to call it NAG, N-acetyl glucosamine, and we turn it into something else. How do we turn it into something else? We add phosphoenol pyruvate to it with the help of an enzyme. Let us give enzymes a different color. What different color? We give enzymes a different color. And that will be this one. Phosphoenol pyruvate is added with the help of the enzyme enol pyruvate transferase. Enol pyruvate transferase. Now on adding this we get N-acetyl muramic acid, that is NAM, and it is done with the enzyme enol pyruvate transferase, and we get what? NAM, N-acetyl muramic acid. Now this will be getting attached to another unit along with a NAG and bactoprenol phosphate. Let us leave this at this part. Let us jump onto the peptide part. Here, the protein part, we have got alanine. L-alanine. It is getting converted into D-alanine. By what? By alanine racemase. This LD conversion is called as racemization, and the enzyme is racemase. Now let me write the enzyme in the separate color. ALA racemase. Now this D-alanine that we have got, this D-alanine is nothing but amino acid. We are going to be joining it into something by using alanine ligase. Alanine ligase. Now we get a chain. Let us better do that chain be in some kind of blue color. Okay, now you have got this NAM and this ALA ligase. Now we are supposed to assemble these. How the assembling occurs? Here, the assembling occurs like this. There is the NAM, a double bond and a NAG. Here we have a triple bond like something, and we have got other peptides about which we have no idea. Then we have got this light blue colored alanine, and we have got another thing which is glycine. We have got glycine. Now this glycine will come here, that is 3 units. This is one total subunit, and this total subunit, this is happening in the cytoplasm, and we want to commit outside the cytoplasm, outside the cell membrane. Now let this be the cell. This be the cell membrane. After this, we have got one brick or one small subunit, which is the building block, and we are supposed to move out these building blocks. And for transporting these building blocks outside, we need a vehicle or we need a transport, and that transport facility is done by bactoprenol phosphate. Bactoprenol phosphate, let it be written as BP, and this one, it needs energy. So bactoprenol bisphosphate or diphosphate. Bactoprenol diphosphate is the energy molecule. It has got two phosphates, and now it can make the whole unit go out. And let that be in another color. Bactoprenol diphosphate. Now this whole unit, let this be going out. Now this whole unit has been transported outside, and I want to paste another one too. uh, Now moving it up here, we have got other previous units transferred. Now on transporting this thing, this bactoprenol diphosphate will lose its energy and become bactoprenol phosphate. Now it is transported back into the cell right now. It is getting transported back into the cell. And as already told, this one thing is a 1 unit of cell wall. This one thing is what? 1 unit of cell wall. After completing this, we get to know that there have been other units too. Now what happens with these other units is that okay, so we have done the forming material formation. We have also done the transportation. This part is the transportation part. This part is the transportation part. Now what we are going to look at is transglycosylation or polymerization part. Transglycosylation or polymerization. So for this, what are we supposed to do? This N-acetyl-muramic acid, right? It will combine. It will combine. So it is called as parallel linking. That part is the transglycosylation or polymerization. And let me do that with one color. And there can also be cross linking possible. This cross linking is supposed to be done by another molecule, and before the cross linking is done, okay, the fourth step is cross linking. Let me write it. The fourth step is cross linking, and for that you need to remove this part which we know, which is d-alanine. This d-alanine, out of which one is supposed to be removed. Let me write this unit here. Actually it is supposed to look something different, but consider this for now. You are supposed to make this 1 unit disappear off, and then you will be getting the cross linking. Let me give another color for cross linking. Light green will do. This cross linking happens between these two. Cross linking with d-alanine, which is present in the fourth place, and this is done cross linking. Now this is the whole process of cell wall synthesis. Now we will see where all we get inhibition. For inhibition we do it with the red color. This inhibition happens, first we will look at this one, phosphoenol pyruvate. Phosphoenol pyruvate, instead of it we use its analogs, phosphoenol pyruvate analogs. And what happens here is competitive inhibition. Competitive inhibition. and the drugs are phosphomycin, phosmidomycin. Phosmidomycin. The next one is we have got D-alanine analogs. The next part is using D-alanine analogs. This is the first one. This is the second one. D-alanine analogs. What are the D-alanine analogs? They block ALA racemase and ALA ligase. So D-alanine analogs are cycloserine. Now when this bactoprenol gets back into the cell for the transport again, it is getting blocked. Here it is getting blocked, and this is done by what? Bacitracin, transport inhibitor of bactoprenol into the cytoplasm. It is bacitracin. Transport inhibitor of bactoprenol into cytoplasm. It is done by bacitracin. Then the fourth one. What is the fourth one? The fourth one is transglycosylation. It is done by the enzyme. I have missed the enzyme. I need to write the enzyme now. The enzyme is peptidoglycan glycosyl transferase. Peptidoglycan glycosyl transferase, and this one is blocked by vancomycin. After this one is blocked by vancomycin, the last one we have got is beta lactams. The last one is beta lactams. Beta lactams inhibit cross linking. So the cross linking is inhibited by beta lactams. Beta lactams are transpeptidase or this penicillin binding protein inhibitors. They block the cross linking. They inhibit transpeptidase or inhibit penicillin binding protein. With this, the total of inhibition drugs gets over. So we are revising it yet again. Fourth one and fifth one. First one is PEP analogs, phosphoenolpyruvate analogs. They are by competitive inhibition of phosphoenolpyruvate by phosphomycin and phosmidomycin. D-alanine analogs cycloserine. Mechanism of action is ALA ligase inhibition, ALA racemase inhibition. Then transport inhibitor is bacitracin. Bactoprenol transport inhibitor back into the cytoplasm. Glycopeptide is vancomycin. Vancomycin, it is a glycopeptide. Vancomycin is a glycopeptide, and its mechanism of action is by transglycosylation or polymerization inhibitor. Then we have got beta lactams, which is transpeptidase or penicillin binding protein inhibitor. It inhibits the cross linking, and the beta lactams are as follows: penicillin, cephalosporin, carbapenem, monobactam. Penicillin, cephalosporin, carbapenem, and monobactam. So these are the drugs used for inhibition. Now we will get into beta lactams. Beta lactams, and that is penicillins. It is so large, so that will itself cover part 1. Now the penicillins of beta lactams. We have got moderate activity, then narrow spectrum, then wide spectrum. So let us get into it. So what are we getting into? Beta lactams, penicillins of beta lactams. Penicillins are grouped into 3 types based on the spectrum: moderate spectrum, wide spectrum, and narrow spectrum. Moderate spectrum, narrow spectrum, and wide spectrum. Moderate spectrum, narrow spectrum, and wide spectrum. Now with moderate spectrum, they act mainly against gram-positive bacteria, and there is limited activity against gram-negative bacteria. Against gram-positive bacteria and limited gram-negative bacteria. Why limited? Because of lower water solubility. Now we have got 3 drugs under this. What are the 3 drugs under this? Yeah, we have got 3 drugs under the moderate spectrum. Moderate spectrum, narrow spectrum, and wide spectrum. This moderate spectrum has got 3, 1, 2, and 3. Penicillin G. First is penicillin G, then is penicillin V, and then long acting penicillin. Penicillin G is otherwise known as aqueous penicillin. Penicillin G is otherwise known as aqueous penicillin. Since it is soluble, it can be used IV, and it is the drug of choice in neurosyphilis. Drug of choice in neurosyphilis. Penicillin V is oral and it is not much use nowadays. Use is similar to penicillin V. Penicillin V similar to penicillin G. The thing is that it's been replaced by amoxicillin and ampicillin. Then long-acting penicillins. Long-acting penicillins are intramuscular. They act like depot preparations. Now the drugs under long-acting penicillin are probenecid penicillin G, procaine penicillin G, and benzathine penicillin G. This benzathine penicillin G acts longer for like 28 days, and it is longer acting and acts as a depot preparation. Now the drug of choice, benzathine penicillin is more important, and it is acting as a drug of choice in rheumatic fever prophylaxis. 28 days, right? 1 month use, once a month use. And then we have got a mnemonic that is slygram positive. So S L Y. S is for streptococcus and syphilis. And for syphilis we have got zero resistance. That is, not even little percent of resistance has been developed against this penicillin G, benzathine penicillin, which are long-acting penicillins. Then we have got leptospirosis, YOS, then gram. And positive is for the mnemonic. G is for gas gangrene. Then R is for rat bite fever. A is for actinomycosis, and M is meningococcus. When for sensitivity positive ones we give in meningococcus. If sensitivity not known, if sensitivity not known, we give what? Ceftriaxone. We give ceftriaxone. If sensitivity is not known, we give ceftriaxone. And narrow spectrum, what we give in narrow spectrum, there is penicillinase resistant penicillin or antistaphylococcal penicillin. See, what happened is that a few developed resistance. So let us see how they developed resistance. For resistant ones, we are giving more and more narrow spectrum ones. Let us see how they picked up the resistance. So the staphylococcus Staphylococcus, what they did is that they developed resistance. How they did is that they synthesized beta lactamase. It is an enzyme which breaks down the beta lactam ring. What they do is this is an enzyme, and what drug we give beta lactams. Penicillin is a beta lactam. What they do to beta lactam is that this is a structure, as we already know. This is the structure of beta lactam, and here we break by giving this beta lactamase enzyme, and hence this beta lactam is broken. It develops a resistance. That is the antibiotic. The antimicrobial does not work. So what we do is that we do a structural modification in the beta lactam ring, so that the beta lactamase or penicillinase or that the beta lactam breaking enzyme becomes ineffective. So that is what we do. So we prepare penicillinase resistant penicillin. We prepare what? We prepare penicillinase resistant penicillin or anti-staphylococcal penicillin. Anti-staphylococcal penicillin. Now this activity is against staphylococcus, which is gram positive. This against staphylococcus, which is gram positive, and we give oral drugs. What are the oral drugs? Oxacillin, cloxacillin, dicloxacillin. So oxacillin, cloxacillin and dicloxacillin are the oral drugs. They are used against these infections. These staphylococci are present in the skin, so it causes skin related infections. So use in mild to moderate cellulitis and mastitis. These are the enzymes in the skin, that is why we are using against them. And the IV drugs, these are the oral drugs, and the IV drugs. For IV, oxacillin, nafcillin, methicillin. Oxacillin, nafcillin, methicillin. Methicillin is nephrotoxic, it seems. Nephrotoxic, it seems. And its uses in severe infections and endocarditis. Then what bacteria did is that bacteria developed resistance against methicillin too. Bacteria developed a resistance against methicillin. Now we get methicillin resistant Staphylococcus aureus, and it has got a mechanism. Alters penicillin binding protein and spread resistance by MEC A gene. Spread resistance by MEC A gene. The drug of choice against methicillin resistant Staphylococcus aureus is vancomycin. Vancomycin. This drug of choice is vancomycin. This MEC-A gene spreads the resistance and it alters penicillin binding protein, methicillin resistant Staphylococcus aureus mechanism, and this penicillin binding protein is totally altered. How is it totally altered? What does vancomycin do? This vancomycin, it prevents the polymerization. It sits in between, so it must bind near to the D-alanine. So where does vancomycin act? Vancomycin acts by binding nearby to the D-alanine, that is here. Vancomycin is a really big molecule. Let us consider this to be vancomycin. Vancomycin is a really big molecule and it wants to bind near to the D-alanine, fifth D-alanine. That is last the last one. Sorry, this is the last one, right? Okay, here it wants to bind here near to the D-alanine, and this is the vancomycin. Vancomycin is really large, and due to the steric hindrance, this bonding is prevented from happening. This bonding is totally prevented from happening. So now this vancomycin, what does it do? This vancomycin, it binds near the D-alanine, so we need to change the D-alanine. The drug of choice is vancomycin for methicillin resistant Staphylococcus aureus. Now there is resistance against vancomycin. This resistance against vancomycin is brought about by changing the last subunit D-alanine into D-lactate. So this vancomycin now cannot bind. So what develops vancomycin resistant Staphylococcus aureus. For this one, we have got drugs of choice, that is daptomycin. And that is daptomycin. The alternatives are linezolid, streptogramins, and tigecycline. Linezolid previously, but tigecycline, it is like tetracycline, but it is not. This was used previously. The tigecycline, it is like tetracycline, but not. Now we have gotten into the wide spectrum ones. This wide spectrum drugs are called as anti-pseudomonal drugs. The main are they are being divided into three. Carboxypenicillin, uridopenicillin, and aminopenicillin. This carboxypenicillin, uridopenicillin are anti-pseudomonal drugs. This carboxypenicillin and uridopenicillin. Carboxypenicillin has got this carboxy group. This carboxy group is positive charge and it has increased water solubility, more water soluble. This uridopenicillin has got a positive and a negative charge, and what they do, they have maximum water solubility. They are the uridopenicillins are most effective against gram negative ones. And the drugs. What are the drugs? The drugs are carbenicillin and ticarcillin. Carbenicillin, ticarcillin. This is azlocillin, maslocillin, piperacillin. And remember this piperacillin and pseudomonal. Then we have got aminopenicillin. Aminopenicillin, it is negatively charged only. And we have got two drugs in it, amoxicillin and ampicillin. Amoxicillin and ampicillin. The thing is that it has got increased oral absorption. This has got less oral absorption. So this has to be more oral absorption, so less dosage, thrice a day. 3 times dosage per day. This is 4 times dose per day. Then this has got increased oral absorption, so less diarrhea, because when the drug is not being absorbed properly, it remains in the lumen and destroys the normal colonic flora. Then it leads to diarrhea only eventually when there is less flora. And the route is through oral or IV, whereas this one is IV. And infection we can cover mild, moderate and severe infection. This can be used only for severe infections only. For uses we have got For uses, we have got what? We have got a respiratory infection. And what we get is otitis and pneumonia. It can also be used in UTI. It is safe in pregnancy. It is safe in pregnancy. Why do we specify pregnancy? Pregnancy is specified because during pregnancy there is increased risk of UTI, and increased risk of UTI happening in pregnancy, it is because of hormonal changes and the pressure by the uterus over the bladder. So, and also it might lead to retention of urine in the bladder. And other uses are IV ampicillin plus gentamicin. We know that ampicillin is as we had previously seen. Sorry. As we had previously seen, what does ampicillin do? Ampicillin, we have got it here, beta lactams. Under that, we have got, under penicillin, we have got ampicillin. Now, here we have got aminoglycosides. Aminoglycosides is bactericidal, and it can be used, it can be combined with these. So, add on drugs, aminoglycosides can be used as add on drugs along with beta lactams. So we know that already, and this is the miscellaneous uses. So IV ampicillin plus gentamicin, it can be used as an add-on drug. So this is used as a drug of choice in Listeria meningitis. And Enterococcus faecalis endocarditis. If no response, we use vancomycin plus gentamicin, because if ampicillin, this penicillin, if it does not work for resistant cases, we use vancomycin. That also we had seen earlier. Then the mechanisms of resistance we had seen here. What are the mechanisms of resistance? Here there is production of that beta lactamase or penicillinase enzyme. They cut the base position of the beta lactam ring, so penicillin G becomes ineffective, and thus we use the narrow spectrum and there is resistance against methicillin by altering the penicillin binding protein, and the resistance is spread using MEK-A gene. For that, the drug of choice is vancomycin, and now the resistance against vancomycin is developed because vancomycin binds to D-alanine and blocks the polymerization, but D-alanine is being changed to D-lactate, and thus vancomycin is not able to bind. So we get vancomycin resistant staphylococcus aureus. The drug of choice for that is daptomycin. With this, cell wall synthesis inhibitors part 1, that is only penicillins, get completed. Thank you.